One of nature's greatest wonders is the ability of the human ear to distinguish among the millions of sounds around us. Listen. Recognize those sounds? Surely. Each sound has a distinctive pitch, loudness, and quality. You will hear later how these characteristics are determined by the frequency, intensity, and form of sound waves in the air. Waves which your ears pick up and analyze. But first, let's investigate what causes sound. The source of every sound is a vibrating body. Take, for example, a drum. The vibrating drumhead pushes against the air every time it moves outward. It shoves the air molecules against other air molecules, compressing the air. This compression moves away as the drumhead moves inward, leaving a region where the air is slightly thinner than normal. On the next outward push of the drumhead, another region of compression is formed and started on its way outward. We call these pulses of compressions and rarefactions pressure waves. As long as the drumhead vibrates, pressure waves will be generated and sent through the air. When waves of sufficient strength reach your ears, they push on your eardrums, setting them to vibrating too. It's these vibrations which your brain interprets as sound. Despite your ear's sensitivity to minute changes in air pressure, it is only when the changes are repeated in rapid succession, at least 20 times a second, that your brain perceives them as sound. On the other hand, vibrations that occur more frequently than about 20,000 times a second cannot be heard by the average human ear. This audible frequency range varies considerably with different people and different ages. Generally, as a person grows older, the delicate membranes of the ears grow stiff. Then it becomes more difficult to hear the very high frequencies. Let's get acquainted with the sounds of different frequencies. Listen as we produce a series of vibrations starting at 30 cycles per second and gradually increase the frequency until it is 15,000 cycles per second. 30 cycles per second. 50. 100. 200. 500. 1,000 cycles per second. 2,000. 4,000. 6,000. 8,000. 10,000. 12,000. 15,000 cycles per second. Your ears are probably most sensitive to vibrations in the frequency range between about 1,000 and 4,000 cycles per second. Changes in atmospheric pressure about 1 part in 10 billion, if repeated about 3,500 times a second, will send an audible sound to your brain. At this minute pressure variation, the eardrum moves less than 100,000th the wavelength of light, 1/10 the diameter of the smallest atom. If your ears were very much more sensitive, you probably would be able to hear the motion of the molecules of the air as they vibrate with thermal energy. Some sounds appear higher or lower to our ears than others. The term we use to describe this relative characteristic is pitch. Pitch depends chiefly on the number of times each second that the air pressure fluctuation on your ear is repeated. Listen as we cause a stretched string to vibrate 440 times a second. Here now is a human voice with vocal cords vibrating at the same frequency. Now listen as we hold a piece of cardboard against a revolving gear. The gear teeth are striking the cardboard 440 times a second. Here are these same sounds again. Notice that the pitch of each sound is the same, although the sources are different. The pitch is the same because the vibrations striking your ears are repeated the same number of times per second. Now, if we double the frequency to 880 times a second, the pitch sounds higher. But the pitch of an 880 cycle tone does not sound exactly twice as high as one at 440. Of course, some persons have been conditioned by their familiarity with musical intervals, such as octaves, to think that doubling or cutting frequency in half is the same as doubling or cutting pitch in half. However, psychological tests have shown that pitch and frequency of pure tones do not have a simple one-to-one relationship. For example, many persons would judge that this tone is one half the pitch of this tone. Although the pitch may sound one half, the frequency is not. The frequency of the higher tone is 500. The lower tone is 200 cycles per second. Apparently, we cannot depend on our ears to determine relative frequency, nor can we use frequency numbers to designate relative pitch. The two are not linearly proportional. Science has, however, worked out a subjective pitch scale for pure tones. The commonly chosen reference frequency is 1,000 cycles per second. The tone you heard is designated to have a pitch of 1,000 subjective units, sometimes called mels, M-E-L-S. Mels from the word melody. A tone with a pitch twice as high is designated 2,000 mels. Actually, its frequency is 3,120 cycles per second. A tone which sounds to our ears 3 times as high as the reference is said to have a pitch 3 times as high, 3,000 mels. Actually, its frequency is 9,000 cycles per second. As you can see, a mel scale provides an objective means for comparing pitches of various pure tones. Although pitch depends chiefly on frequency, it also varies slightly with the loudness of a sound. Listen as we play 2 pure tones, one softly, then one loudly. Which tone has the lower pitch? Actually, both tones have the same frequency, 200 cycles per second. But the louder tone sounds a little lower pitch to most persons. In fact, experiments have shown that in general, low-frequency tones seem lower pitched when played very loudly. On the other hand, high-frequency tones seem higher pitched when played very loudly. To be sure, the difference in pitch is very slight. Nevertheless, it is discernible to some persons. Sound vibrations may be generated by many different sources, whether they originate in the orifice of a modern jet engine or the throat of a 400-year-old tortoise calling its mate. Or an electrical buzzer, the vibrations have essentially the same effect. They fluctuate the pressure of the atmosphere on our eardrums, causing them to move rapidly back and forth. This pressure variation is measured in terms of a unit called a microbar, which is 1 dyne per square centimeter. We can decrease the pressure variation and thereby make the sound less intense by decreasing the amplitude of the source's vibrations. Listen as we decrease the power of the buzzer. If we increase the power, the sound intensity will increase. What we are doing is varying the amount of sound energy which stimulates your ear each instant. This can be accomplished another way, too, by varying the distance the pressure waves have to travel to your ear. If we move our microphone away from the source, the intensity will decrease. If we move our microphone closer to the source so that the energy has less distance to travel to your ear, the intensity will increase. Intensity may also vary according to the characteristics of the room in which you are listening. If we play a pure tone of constant intensity, you can, by moving your head slightly to the right and left, make the sound seem less or more intense. Try it. This phenomenon occurs because sound waves that have been reflected from the walls interfere with sound waves that are coming from the loudspeaker. They combine to produce pressure waves that seem to stand still, thus forming areas of high and low intensity in the room. However, ideally, in free space where there are no reflecting walls, the energy at your ear will vary inversely as the square of your ear's distance from the sound source. Listen. I am now speaking to you from a distance of 1 foot from the microphone. I am now speaking to you from a distance of 3 feet from the microphone. You see, by making a sound travel 3 times as far, we have decreased its intensity to about 1/9. Listen again. I am now 1 foot from the microphone. I am now 3 feet from the microphone. To sum up, the intensity of a sound depends chiefly on the energy of the source and its distance from your ear. Thus, intensity may be measured in energy units, ergs per square centimeter, or converting to power units, in watts per square centimeter. For most purposes, however, it is more useful to measure the intensity of sound on a comparative scale. It's customary to express this relative intensity in a unit of measure called a bell, B-E-L, bell, named after Alexander Graham Bell. Listen to these 2 sounds. They have an intensity difference of 1/10 of a bell, 1 decibel. As you heard, a difference of 1 decibel is so small as to be barely perceptible. If one tone has 1/4 the power, that's 1/2 the sound pressure of another, it is said to be 6 decibels less intense. If one tone has 1/16 the power, or 1/4 the sound pressure of another, it is said to be 12 decibels lower. If one tone has 1/100th the power, or 1/10 the sound pressure of another, it is said to be 20 decibels less intense. As you can see, the decibel scale is logarithmic, and the decibel expresses a relative quantity, the ratio between 2 acoustic powers. When it is desired to express the intensity of only one sound, a scale is used in which the reference intensity for 0 decibels is 10 to the minus 16 watts per square centimeter. A person with very good hearing in an extremely quiet location can just barely hear a 1,000 cycle tone at this 0 level of intensity. The corresponding pressure variation is only about 0.0002 dynes per square centimeter. That's less than 1/billionth normal atmospheric pressure. You see, then, your ear is extremely sensitive. So that you can become familiar with the decibel scale, listen as we vary the intensity of my voice. Now I am speaking to you in a voice with an intensity about 6 decibels lower than normal. Now my voice has an intensity level about 10 decibels lower than normal conversation. 20 decibels less intensity sounds like this. 30 decibels less intensity sounds like this. Did you ever notice how the pitch of a train whistle suddenly lowers as the train rushes past you? Or if you are on a moving train going past a clanging crossing bell, how the bell's pitch changes. These are 2 examples of a phenomenon called the Doppler effect, in honor of the Austrian physicist Christian Doppler, who first explained it in 1842. What happens is this. When you are on a moving train approaching the clanging bell, you are actually meeting the sound waves before they would ordinarily reach you. So more sound vibrations impinge on your ear each second than if you were not moving. Consequently, your eardrum is made to vibrate faster, giving you the impression of higher pitch. When you are moving away from the bell, in effect, running away from the sound waves, fewer vibrations reach you during any interval, and the pitch that you hear is lower than it would be if you were not moving. Listen again. In the case where you are stationary and the train whistle moving, the sound waves ahead of the whistle are crowded together and made shorter, while the waves behind the whistle are spread out and made longer. This change in wavelength does not change the speed with which the waves travel, but it does change the number of waves that hit your ear in a second. So, as the train approaches you, more vibrations per second reach your ear, and you hear a higher pitch than you would if the whistle wasn't moving. And as the train goes away, fewer vibrations per second reach your ear, and the pitch you hear is lower than it would be if the whistle wasn't moving. Here is another example of the Doppler effect. Racing cars. The roar of the first car you heard changed pitch almost a musical fifth as it passed close by. The slower cars, bringing up the rear, changed pitch about a minor third. Obviously, the Doppler effect can be used to measure the speed of a sound source. The greater the change in pitch, the faster the source is moving. The old proverb, empty vessels make the most noise, is an ancient observation of the phenomena of echo and reverberation. When sound waves impinge on hard surfaces, they are reflected. Often we may hear the reflected waves or echoes a short time after we hear the original source of the sound, like this. Hello. 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 Are you there, echo? The time lag between the original sound and the echo depends upon the distance between the sound source and the reflecting surface. Here is how speech sounds accompanied by echo from reflecting surfaces at various distances. 500 feet. You are now listening to speech accompanied by an echo from a reflecting surface 500 feet away. 200 feet. You are now listening to speech accompanied by an echo from a reflecting surface 200 feet away. 50 feet. You are now listening to speech accompanied by an echo from a reflecting surface 50 feet away. The echo sounds fainter than the source because the original sound energy is spread out and lost, traveling to and from the surface. It's quite possible for echoes to have echoes. Large auditoriums or halls, like empty barrels, often have more than one reflecting surface. sounds may bounce from wall to wall. That is, reverberate, like this. Hello. 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 Hello, ladies and gentlemen. When echoes are numerous and overlapping, they may merge into a babble of noise, making normal speech difficult to understand. Hello, ladies and gentlemen. I am sitting in a hall that reverberates with many echoes. Biblical legends tell us that inside the famous Tower of Babel, even the words of learned men sounded like nonsense. This could have been a case of poor acoustical design. The tower was made of sun-baked bricks and tiles, which reflected sounds from one wall to another, setting up reverberations that scrambled speech until it was unintelligible. Reverberation is responsible for the slowness with which sound fades away. It may be controlled by carefully selecting wall materials and coverings to absorb the sound energy. The time it takes a sound to diminish 60 decibels, or 1/1,000,000th of its original intensity, is called reverberation time. We use reverberation time as a measure of the acoustic characteristics of a hall. Listen. I am now speaking in a room that has a reverberation time of several seconds. Rooms which have a reverberation time of several seconds or more may be suitable for some forms of music, but generally they are undesirable for speech. Reverberations fade away more rapidly in small rooms because it takes less time for the sounds to bounce back and forth between the walls and be absorbed. I am now speaking to you in a room which has a reverberation time of only a few tenths of a second. Rooms which are moderately reverberant, that is, having reverberation times of about 1 second for a small auditorium and about 2 seconds for a large auditorium, are usually pleasant for both speakers and listeners. I am now speaking in an auditorium that has a reverberation time of about 1 second. This auditorium has been specially designed to give satisfactory acoustics no matter where the listener is sitting. As you can hear, speakers rely on some reverberation to give resonance and sustenance to their voices. If you've ever sung in a bathtub, you will understand how reverberation may make a voice sound better than it really is. When speech or music is transmitted along communication lines, sometimes the various frequencies may not travel with equal velocities. They arrive at the receiving end with a type of distortion known as delay distortion. This sounds similar to the following demonstration in which frequencies above 3,000 cycles are delayed 1/10 of a second behind frequencies lower than 3,000 cycles. The upper frequencies of this speech are arriving 1/10 of a second later than the lower frequencies. That much delay distortion rarely occurs. Here is how a delay of 7/100ths of a second sounds. The upper frequencies of this speech are arriving 7/100ths of a second later than the lower frequencies. Now listen to the effect of a delay of 35,000ths of a second. The upper frequencies of this speech are arriving 35,000ths of a second later than the lower frequencies. In transmitting music, the distortion that results from small delays or phase shift is usually not noticeable. This is because the various sounds are sustained longer in music than in speech. Listen as we delay the upper frequencies of music 7/100ths of a second. On the other hand, longer delays are quite noticeable in music. They give an echo effect. Listen as we play the same selection so that frequencies above 3,000 cycles are delayed 3/10 of a second. That was the sound of a tuning fork. It is practically a pure tone. That is, the vibrations are of only one frequency, and they have a smooth, regular waveform. Sounds from other sources, such as musical instruments, the human voice, or noises, have waveforms that are less smooth and more complicated. For instance, if we pluck a stretched string, it will vibrate not only as a whole, but also at the same time in parts, in segments that are a half, a third, a fourth, and so on of the whole string. These segments vibrate at 2, 3, 4, and so on times the frequency of the entire string. Listen. The lowest frequency present in a complex sound is called the fundamental. Frequencies higher than the fundamental are called overtone frequencies. The frequencies of a musical sound are simple multiples of the fundamental and are called harmonics. For instance, the fundamental frequency of the musical tone you just heard was 200 cycles per second. The first overtone, sometimes called the second harmonic, was 400 cycles per second. The second overtone, or third harmonic, was 600. The third overtone, or fourth harmonic, was 800 cycles per second. And so on at intervals of 200 cycles per second. Some sounds have 30 or 40 overtones in the audible frequency range of the human ear. For many sounds, the pitch of the entire tone is the same as that of the fundamental, but the overtones add distinctive qualities. Listen as we play a fundamental tone and then add its overtones one by one. Did you notice? A fundamental with only a few overtones sounds empty and uninteresting. A fundamental with many overtones sounds full and rich. It's the relative number, pitch, and intensity of a sound's overtones which determine its quality. All sounds have characteristic qualities which your ear learns to recognize. Listen. We're sure you had no difficulty distinguishing these sounds. A factory whistle, a soprano, and a piano, even though they all have the same pitch and intensity. That's because the distinguishing characteristics of a sound, by which we recognize an instrument or a voice, is due largely to the proportions of the overtones in the sound, as well as its pitch and intensity. Listen as we play the same sounds, only this time we will filter out the overtones and allow only the fundamental notes to reach your ears. The slight difference in the sounds is due to their dynamic characteristics, such as attack and decay, and vibrato, but the tonal qualities are almost indistinguishable. Listen again. Now we'll allow you to hear the fundamental and the first overtone. We will filter out all the other overtones. Notice just the beginnings of a difference in tonal quality. Now we'll allow the fundamental and first four overtones to reach your ear. Listen how the overtones help distinguish a sound. If we cut out all filters, permitting all overtones to be heard, the sounds will again sound normal and distinctive. If for any reason your ears are prevented from vibrating throughout the entire normal range of frequencies, either because they have some physical defect or because the phonograph equipment is of low fidelity, sound quality will be quite different from normal. Listen to the orchestra as it might have sounded on an early phonograph record. By means of filters, we eliminated high and low frequencies and allowed only those frequencies between about 375 and 2,000 cycles per second to be heard. Now listen to the improved tonal quality when all frequencies reach your ears. If we cut out only the low frequencies, all those below 375 cycles per second, the music sounds like this. Now we'll cut out all frequencies below 2,000 and let only the higher frequencies get through to your ears. If we eliminate high frequencies, all those above 4,000, and let only the lower frequencies through, the music sounds like this. Now let's cut out some more high frequencies. All those above 2,000 cycles are prevented from reaching your ears. Here again is how the orchestra sounds with the full range of frequencies. Speech, too, sounds different if some of the frequencies are prevented from reaching the ear. My voice is now coming through with a normal range of frequencies. Now my voice sounds as it does because we have filtered out all frequencies below 375 cycles per second. Only those frequencies above 375 cycles per second are reaching your ear. If we allow only those frequencies above 2,000 cycles per second to reach your ear, my voice sounds like this. And here's how my voice sounds with all frequencies above 2,000 cycles eliminated from it. You are now hearing only those frequencies below 2,000 cycles per second. Now we have filtered out all frequencies above 375 cycles per second. Here's how my voice sounds if we eliminate both very high and very low frequencies. If we allow only those frequencies between 375 and 2,000 cycles to be heard, my voice will sound like this. As you can hear, there is quite a difference in the quality of the filtered voice and the normal voice that you are now hearing.